Hello everyone. In this video I am going to discuss about the ionization method we use in mass spectrometry. In our previous lecture I have discussed about the first component of mass spectrometry, that was the sample inlet, which convert our sample to vapor phase, because we are injecting sample as a liquid solid and then sample inlet convert that to vapor. And then, as you know, we cannot control neutral molecules, so we have to convert it to ions. That's why we are converting it into ions first before analyzing the mass of our sample. So let's see what method we use for ionization. So first method we use for ionization is electron ionization. So the simplest and most common method for converting the sample to ions is electron ionization. In EIMS or electron ionization MS, a beam of high energy electron is emitted from a filament that is heated to several thousand degrees Celsius. This high energy electron strikes the stream of molecule that has been admitted from the sample inlet system, and the electron molecule collision strips an electron from the molecules and creating a radical or radical cation. You can compare it with a wall. When you are just putting a hammer on a wall, some bricks coming out from the wall. It's very similar to that. When you bombard a molecule like a neutral molecule with electron, if high energy electron is coming out from the molecule, it does convert molecule to radical cation. And further bombardment of electrons, because you are not stopping that bombardment, is converted to radical and cation. So radical cation or cation is useful for us because mass detector can detect only to ions, not radical or to neutral molecules. Now a repeller plate which carries a positive electrical potential direct the newly created ions towards a series of accelerating plates, and a large potential difference ranging from 1 to 10 kilowatts applied across the accelerating plates produce a beam of rapidly traveling positive ions which focused onto the detectors. Now you have to note that most of the sample molecules are not ionized when you are bombarding it with electrons, but are continuously drawn off by vacuum pump. Means when you bombard your neutral molecules with electrons, only some part of sample molecule is converting to radical cation. The part which is not converting to radical cation is drawn off by vacuum pump, which is connected to the ionization chamber. And some of the molecules are also converted to negative ions through the absorption of electron, because every time it's not necessary that electrons is removing from the molecule. Sometimes it can also absorb the electrons, and when it absorbs the electrons, it will have the negative charge. So in this case, because we are using only plates, those can pass only the positive ions, but it can abstract the negative ions. So in this case, the absorption of negative ions will be happen through the repeller plates. So finally we will have only cations and radical cations. Those are going towards the mass analyzer or mass detector. This method has also several advantages and disadvantages. First, we will see what are the advantages. So electron ionization hardware is very inexpensive and robust, and the fragmentation pattern of a compound is reproducible, and many libraries of EIMS data are already available. So this allows one to compare the mass spectrum of a sample compound against thousands of data sets in a spectral library in a few seconds using a computer. So thus simplifying the process of determining or confirming compound's identity or its molecular weight. But this method also has few disadvantages. There's the excess kinetic energy which are coming from electrons imparted to the sample during the EI process leads to significant fragmentation of the molecular ion. So means that is not stopping here, that is going further towards the fragmentation also. Thus one cannot determine a compound's molecular mass in such cases. So another drawback to EIMS is that the sample must be relatively volatile, so it can come into contact with the electron beam in the ionization chamber. This fact coupled with the fragmentation problem make it difficult to analyze high molecular weight compound and mostly biomolecule using EIMS. So these were the disadvantages of this method. Now this is the second method we use for the ionization of sample, which is chemical ionization. So in this technique, the sample molecule are combined with a stream of ionized reagent gas that is present in great axis relative to the sample. When the sample molecule collide with the pre-ionized reagent gas, some of the sample molecule are ionized by various mechanisms which we will discuss here, such as proton transfer, electron transfer, and adduct formation. Almost any readily available gas can be used as a reagent gas for CIMS. The common reagent gas we use for this chemical ionization method is methane or ammonia. So when methane is used in the chemical ionization chamber, the predominant ionization event is proton transfer from a CH5 plus ion to the sample. So let's see how this CH5 plus form. So first this methane absorb the electron and convert it to this radical cation. Now this ammonia radical cation will collide with another molecule of methane and convert it to CH5 plus. Now this CH5 plus is important to ionize the sample molecules. Another reaction can be happen here, that this CH4 radical cation can dissociate to CH3 plus and H radicals. Now this CH3 plus will collide with another molecule of CH4 and convert it to C2H5 plus. So finally this CH5 plus and C2H5 plus are important to convert our sample molecule to ions. So now this CH5 plus collide with M is our sample molecule, and converted it to M plus H, means it's doing proton transfer. Second, when M collide with C2H5 plus, it make M plus C2H5, means adduct formation. In both cases, cation is forming. Now mass analyzer can detect it, or we can control it. Now, but in mass spectrum, we will get a peak of M plus H or M plus C2H5, not M plus. Now, if we use ammonia as a chemical ionization gas or reagent, so first NH3 will absorb an electron and convert it to this ammonium cation. Now this ammonium radical cation will collide with another ammonia molecule and convert it to this ammonium ion. Now this ammonium ion will collide with our sample molecule and then convert it to M plus H by proton transfer. So now in mass we will detect the mass of M plus H instead of the mass of our molecular ion. But as a practical note, spectra required under CI condition are usually acquired over a mass range above the M by Z of the reagent gas ions, because we are using these gases in axis. So if you don't do it above the mass of the reagent gases, you will also see a significant peak of the mass for these gases. So the ionized reagent gas is also detected by the spectrometer, and because the reagent gas is present in great axis relative to the sample, its ions would dominate the spectrum. So the main advantage of CIMS is the selective production of intact quasi-molecules, that is M plus H, means you will get the mass of your molecule instead of fragments of your molecule, which was the disadvantage of EIMS method. Now third method, which is very modern method, is electrospray ionization. So this is one of the soft ionization technique to get the mass of molecular ion or biomolecules. So this is very soft technique. We can also use this technique for biomolecules or peptides. So in ESI or electrospray ionization method, a solution containing the sample molecule is sprayed out of a fine capillary into a heated chamber that is at nearly atmospheric pressure. The capillary through which the sample solution passes has a high potential across its surface, and small charged droplets are expelled into the ionization chamber like this. The charged particles are subjected to counter flow of a drying gas. Usually we use nitrogen gas as a drying gas here, that evaporates solvent molecules from the droplets and converted them into small droplets, at which point the droplets break apart into smaller droplets, and this process continues until solvent free sample ions are left in the gas phase. So finally we are getting ions here. Negative ions may also be formed in this method by loss of protons from the sample to basic species in solution, and the charge transfer of the sample molecule arises from a combination of charge concentration in the droplets during evaporation of the aerosol or cloudy form, and the electrochemical process stemming from the electrostatic potential of the capillary here. So this is the electrospray ionization method to convert the sample into ions, and this is a very soft technique. Now fourth technique is desorption ionization method. So there is a various desorption method. Here I am discussing about two main methods. First is a fast atom bombardment, that is known as FAB, and second is a matrix assisted laser desorption ionization method, which is also known as MALDI. So the modern techniques such as FAB and MALDI allow the analysis of large non-volatile molecules such as biomolecules, and these methods are desorption ionization technique. In desorption ionization, the sample to be analyzed is dissolved or dispersed in a matrix and placed in the path of high energy beam of neutral atoms or high intensity photons. So if we are using FAB, then we use neutral atoms, and if we are using MALDI, then we use high intensity photons. So beam of neutral such as argon or neon atoms are common in FAB, and most MALDI spectrometer use a nitrogen laser that emits at 337 nanometer. Now the collision of these atoms or photons with the sample ionize some of the sample molecules and eject them from the surface like in this way, and the ejected ions then accelerated toward the mass analyzer as with the other ionization method. So it's very simple, just you loading your sample on the matrix and just bombardment it with the beam of neutral atoms or photons, then they will emit them and ionize them in this form, and then they will go towards the mass analyzer as we have discussed in previous methods. Now the matrix should be non-volatile, because matrix also should have some properties here, and one of the important properties, it should be non-volatile, because if you using beam here, it should not be evaporate, and relatively inert and a reasonable electrolyte to allow ion formation. The matrix compound used in MALDI are chosen for their ability to absorb the ultraviolet light from a laser pulse, that is 337 nanometer for N2 laser, which is we mainly use in MALDI technique, and substituted nicotinic, picolonic and cinnamic acid derivative are often used in a MALDI technique as a matrix. So these were the different methods for the ionization we use in mass spectrometry, and which is the second component of mass spectrometry technique. And thank you very much.